US Physics Olympiad, year 2020, USAPHO, final round. Problem B3. Real expansion. Consider a real monatomic gas consisting of n atoms of a negligible volume and mass m in equilibrium inside a closed cubical container of volume V. In this real gas, the attractive forces between atoms is small but not negligible. Because these atoms have negligible volume, you can assume that the atoms do not collide with each other for the entirety of the problem. Question A. Consider an atom in the interior of this container of volume V. Suppose that the potential energy of the interaction is given by 0 when R less than D and negative epsilon multiplied by D over R power 6 when R greater or equal D, where D much less than V power 1/3 is the minimum allowed distance between two atoms. Assume the gas is uniformly distributed with the container. What is the average potential energy of this atom? Write your answer in terms of A prime equal 2 pi d cube epsilon over 3 n and V. Question B. What is the average potential energy of an atom near the boundary of the box? Assume that there is no interaction between atoms near the boundary and the box itself. Question C. Using Bernoulli's law, P plus U plus rho V square over 2 equal constant with the pressure P, potential energy density U, mass density rho and the fluid velocity V. What is the pressure at the boundary of the box? Assume the interior pressure is given by the ideal gas law. Question D. Assuming most atoms are in the interior of the box, what is the total energy of the atoms in the box? Now consider an insulated partitioned container with the two sections, each of volume V. We fill one side of the container with the n atoms of this real gas at temperature T, which the other side being a vacuum. We then quickly remove the partition and let the gas expand to fill the entirety of the partitioned container. During this expansion, the energy of the gas remains unchanged. Question E. What is the final temperature of the gas after the expansion? Question F. What is the increase in the entropy of the universe as a result of this free expansion? Give your answer to first order in A prime n over V kb T. Solution for problem B3. Question A. The density of the gas is given by n over V. In a spherical shell of radius r and the thickness delta r, there are number of atoms 4 pi r square delta r multiplied by n over V. The potential energy is given by this expression. Then the potential energy is given by integral from d to infinity, which is this one. And after integration we have this expression, which is in terms of A prime n and V equal negative 2A prime n over V. That was solution for question A. Solution for question B. Now only half of the shell of radius r is full of gas and the other half is outside of the box. This means that the potential energy is lessened by a factor of 2. So we have answer negative A prime n over V. So that was a solution for question B. Solution for question C. The potential energy difference for the one atom was negative A prime multiplied by n over V. It means that the potential energy density difference is this one, which is negative A prime multiplied by n square over V square. Since there is no velocity difference, this is also the pressure difference. And due to universal gas law, we have PV equal nKT, where n is concentration of molecules, K is Boltzmann constant, and T is absolute temperature. So it means that n equal n over V, and we have pressure inside the box is nKT over V. Then pressure on the box is this expression, pressure inside the box. So that was a solution for question C. Solution for question D. The total kinetic energy all molecules inside the box is 3 over 2 nKT. The total potential energy is potential energy for one atom multiplied by number of atoms, and we drop the factor 2 to avoid double counting. So we have potential energy equal negative A prime n square over V, and the total energy is this expression. That was a solution for question D. Solution for question E. In previous question we counted that total energy is this expression, and because energy is conserved, we have this equation to find what is final temperature. Here on the left we have volume is V, and on the right we have volume 2V. And from here we have new temperature T prime equal T minus A prime n over 3 kV. That was a solution for question E. Solution for question F. The entropy of the surroundings do not increase as a result of the free expansion. No heat is dumped to the surroundings, and the surroundings remain in thermal equilibrium. However, the entropy of the gas does increase because the gas is momentarily not in equilibrium. Therefore, we just have to compute the increase in entropy of the gas. Because entropy is a state function, we compute this change in entropy by constructing a reversible process between the initial and the final states of the expansion, and computing the change in entropy for this process. Consider constant energy reversible expansion of this gas. For this process, the work done by the gas is equal to the heat the gas takes in. Therefore, change of entropy ds equal dq over t, or equal p dv over t, where we use lowercase letters to denote the quantities during the reversible expansion. Recall that from previous we have this expression. If energy of system is E, we have this expression which is simplified to this. And from here we can express P and T as a function of V. Now we can do integration. So by definition, change of entropy delta S equal integral from V to 2V from this expression, and after substantiation P and T we got this one, and after Taylor expanding we got this expression, and this expression we can do full integral, which is this one, and energy approximately equal to 3 over 2 nKT. Finally we got change of entropy is this expression, which is answer for question F. We made all problem B3.